Well, good morning or good afternoon, everyone, depending on where you are. And welcome to our WebEx today. We're going to be talking about material characterization and testing, and in particular about fatigue characterization. So where do all those fatigue properties that you put in software, where do they come from, and how do we test them? They say we learn best from our mistakes. So it's typical, really, to start a fatigue presentation with one of the best lessons. And my favorite lesson that I like to talk about is the story of the de Havilland Comet. So for those who aren't aware, the de Havilland Comet was the first commercial jet airliner. It first flew in 1949. And despite all the problems that we'll be looking at today, it was actually quite successful. Its final commercial flight was in 1997. And if we were to include the military variant of this, which was the RAF Nimrod, then the final flight in Nimrod with the same airframe was in 2011. So it had quite a long life. In terms of aircraft, it was 10 years ahead of its competition. The Boeing 707 first flew in 1958. So remember, this was 1949. So as such, compared with other airliners of its time, it was quite revolutionary. It flew twice as fast as any other commercial aircraft, about 500 miles an hour. And for comfort as well as economy, it flew much higher than any other aircraft too. So 40,000 feet was normal. And that was in order for economy of the jet engine, but also for comfort of passengers, because you didn't get buffeted by all the turbulence and things. So Geoffrey de Havilland, whose company it was, had big plans for the Comet. He'd taken his design cues from modern rail travel, and he wanted it to be the poshest way of traveling, the most comfortable. So he created large panoramic square windows so people could see out of it. Of course, because it flew so high, it was the first airliner to have a pressurized cabin. And it also pioneered the use of stressed skin construction. So it used both rivets and adhesive in its construction. Its fuel tanks were mounted in the wing cavities, again another first, and because of the speed and the aerodynamic loading, it was the first passenger aircraft ever to use power-assisted flight controls. Strangely enough, they were hydraulic controls at that time, even though the hydraulic fluid, of course, is quite heavy. Again, we found very early on in two initial accidents that pilot feedback was a problem. The pilot couldn't feel the control surfaces through the control column. So again, it was the first aircraft ever to have a simulated control feedback loop called Q-Feel. And when we look at it, it really arguably set the design standards for every aircraft up until today's composite aircraft that we're seeing. Of course, when you're doing so much that's new, you have a lot of obstacles to come across too. And the biggest challenge in the Comet was weight. Weight was at an absolute premium. And the reason for this was because there weren't many jet engines around at the time. And de Havilland wanted to use their own jet engine. A few years before, they bought a jet engine company, and they were desperate to use their own engines. These de Havilland Ghost turbojet engines could only deliver 5,000 foot-pounds of thrust. And this really wasn't enough for the Comet. In fact, the original design also included two Sprite booster rockets in order to get it off the ground. But thankfully, they weren't required by the first flight. Obviously, noise abatement regulations weren't too hot in those days. But the problem with the weight was that it also needed to use really thin fuselage skin. So this stress skin fuselage was made of 22 gauge aluminium. That's 0.64 millimeters thick for those in metric, extremely thin. And the reason the Comet was unpainted with this beautiful silver finish wasn't because it really looked pretty, it's because the paint weighed too much and they couldn't afford to lose the payload capacity. So they didn't paint it in order to save the weight. Of course, when you're introducing so much which is new, there are things going to go wrong. And the Comet is famous or infamous for two tragic fatigue failures. On the 10th of January in 1954, on a flight from Rome, the aircraft Yoke Peter crashed into the sea. All 53 passengers were killed. And the initial conclusion was that it was a fire, an explosion in midair, possibly even by a bomb. So they never went on to really look much further. But less than 3 months later, on the 8th of April, same year, again on an aircraft flying from Rome, the next aircraft, yoke, crashed over land. All 21 passengers were killed in that. And at that point, the aircraft was grounded for further investigation. And what followed was really the largest crash investigation ever undertaken at that time. The debris from the second crash was so destroyed that they couldn't really use it. So they decided to do a sea recovery of the first aircraft. So they went through to the crash site over the sea. They recovered as much of it as they could, which was actually a substantial part of the fuselage. And we can see here in this bottom picture, we can see these are two windows, if you like. These are the ADF aerials on the top of the roof. And we can start to see where fatigue crackings developed. And in that top picture, you can see an artist's illustration here from Channel 4, where you can see the cracks starting at those re-entrant corners and growing to form the collapse. In order to investigate this failure, they created a thing called the water torture test. And the picture you can see here on the left was at the RAE research facility. And what it was they took a fuselage from a real aircraft. This was Yoke Uncle, the third aircraft. It had already done 1,230 real flights. And what they did was they build it up in this water pressure jacket, and they changed the water pressure internal in order to represent the ground air ground pressure cycles. And after just 1,800 simulated pressure cycles, meaning a total of 3,000 ground air ground cycles, then the fuselage failed, as you could see in that right-hand picture there. So based on a factor of safety of about 3, for fatigue, which was thought at the time, then the fatigue life of the aircraft was put somewhere between 1,000 and 9,000 flights. And actually, when we look at the first aircraft, then that failed not long after that number of flights. Now, of course, when we look at this in the history books, most people start to think about failure as being the square windows of the Comet. And later on, the next marks of the Comet, they had oval windows put in. And there are other things too, like the skin thickness was changed, this frame and stringer spacing was changed, and so on. But although the square windows were often seen as being the cause, it's a bit disingenuous, really, to blame de Havilland engineers for that, because they were aware of the stress concentration. They knew that, and they'd taken that into account during the design. It's true in those corners there are higher stresses, but that shouldn't have caused the failure. What really caused the failure of this was more down to the bonding arrangements. So the original aircraft was designed to have redox bonding and drilled riveted construction around the windows. But the actual production used punch rivets with no bonding around the windows because it was too difficult to get the detail in. And this ultimately led to the failure. So if we look at these material curves, this is an SN curve, if you like. So the y-axis is stress, and the x-axis is cycles to failure on the log axis. If we were to take a joint of just rivets and we were to test them in fatigue, we get that quite steep dotted red line. So if we know the stress, we can look along and it will tell us how many cycles to failure there are. And that's quite a steep one. It's quite strong. It'll take quite a lot of load, but it still always has a fairly short fatigue life. If we compare that, though, with the redox bonding, which is the blue line, we see that's fairly shallow. What this means is when the stresses are high, then there's very little fatigue resistance. It will fail almost straight away. But when the stresses are below, then it will have a very long fatigue life, almost ignoring fatigue. The benefit of having a hybrid of both is that effectively you almost join the two together. So for most of the aircraft loading, then you'll get a long life because the bonding takes the fatigue. But if you get some things like serious crash landings or high impact when the bonding would usually fail, then the drilled rivets take over. They hold the bonding in place So we get the best of both worlds. We get a nice, strong fatigue structure. But the real production aircraft used punch rivet joints with no bonding. Now, a punched rivet isn't as good as a drilled rivet because in punching, we create a lot of anomalies and flaws around the hole, and they create starter cracks for fatigue cracks to initiate. Whereas if we drilled them, we end up with a nice smooth finish. So the punched rivets aren't as good as the drilled rivet, and the fact there was no bonding meant that the real fatigue life was orders of magnitude lower than the original design called for. So this is showing really from that lesson how important it is to understand our materials, and also how important it is to make sure that those on the production line are aware of all the design implications taken right back at the beginning. Now, fatigue testing wasn't new to the Comet. It was actually, as we see here, pioneered in the 1850s by August Woerner. August Woerner was a German railway engineer, and he invented the very first fatigue test rig, which you can see this illustration here. Now, Woerner was interested in looking at fatigue of rotating axles on the train. So in this rig, you can see the S and SY, they're two axles. He was very efficient in the use of testing two at the same time. The springs P allowed us to introduce bending into those axles, and then the pulley system at D would be attached to a motor, and that would rotate the axles. Now, Woerner was very smart. He was also invented the first data logger as well, because by an arrangement of string and pen, he was able to attach a data logger so that he could count how many cycles it had taken before it failed too. So all in all, he was a very smart guy. What Woerner was really interested in is a parameter which he called the fatigue strength. So despite how strong the material is, if you've got constant variable amplitude load, such as you see in an axle, what you found was that the actual strength was much lower than the theoretical strength of the material. And what he was interested in doing was finding that strength, finding that stress below which fatigue was never an issue. And that was what we call the fatigue strength. It was later on that another guy called Baskin came along, and he found that if you were to actually plot the real measured life on a log plot, then you've got now stress versus cycles to fail on a log plot. You could draw a straight line through that. That guy's name was Baskin, and we call that the Woerner line because he used the Woerner test in order to generate it. And we see quite clearly with this Woerner line how it comes down at a nice straight line, and then it kinks off and it goes almost to infinity, where we get that fatigue strength limit that Woerner was originally looking for. Of course, now we realize that an infinite life doesn't really exist. An aluminium alloy, for instance, looks more like this. It has two distinct gradients. One we call post-endurance at that high life, but it's still not infinite. It's not flat. It's just shallower than the other. And even steel, when you've got variable amplitude loading, does not show infinite life. It shows a much reduced slope, as we see here. Of course, the rigs that we use today, we still use Woerner's rotating bend, but most of the tests that we do tend to be axial. So the one on the left here, you can actually see this is a strain control test on bar stock. You can see the hourglass specimen in the middle being tested here. And on the right, you can actually see this is actually a thin sheet. That clamp thing arrangement that you see is actually an anti-buckling guide. So when we go into compression, we don't buckle the thin plate. And you can't see the clip gauge on the other side of that, but you see the clip gauge in the left-hand illustration here. That one's showing us the strain and the gauge section of the specimen. So if we were to look at a rig, my colleague here was holding this panel so I could take a photograph of it. This shows the typical sort of rig. So if we look on the right-hand plot, and we'll go from the bottom upwards just to explain what they are. We start off with a hydraulic actuator. So this is basically a hydraulic ram that can push compression and tension into the specimen. Alongside that, we have an LVDT. It's a linear variable displacement transducer. This measures the displacement that's going into it, how far it's moving. We've then got our specimen in the middle, and attached to that is the clip gauge extensometer, and this is used for strain life. It's measuring the strain in the gauge section of the specimen. And then as we move to the top, we've got a load cell. This is measuring the load which is being transmitted through the specimen. Now, it's important when we do this that we align the specimen perfectly. We don't want to introduce bending and things like that. So on this particular rig, what you're seeing here is what we call a Woods metal pot. So Woods metal is a low melting point metal, very similar to solder. What we do is we heat it up, it melts, we can then lower the specimen in there on its clamps, and then we can pass water through it to solidify it. And that allows us, in this case, to get a perfect alignment. So when we pass load through it, then there's no eccentricity. There are other types of grips as well that you'll see, but for this one, we're using Woods metal. Now, those three transducers, we can log those, and that's what we use when we're doing our analysis. So we can have a separate trace of display